Hello, everyone. Today we'll talk about the concept of entropy and its connection to the concept of mutual information and how both of these concepts are employed in machine learning applications. So we'll start first with an introduction to the concept of information and its link or relationship with uncertainty. So information theory is the scientific study of the quantification, storage, and communication of digital information. The field was established by Harry Nyquist and Ralph Hartley in the 1920s and Claude Shannon in the 1940s. A cornerstone of information theory is how we quantify information that exists in a message. So a key measure to quantify the information in information theory is called the entropy. And entropy is generally defined as a measure of uncertainty associated with a random variable. So the idea over here is that the more uncertain we are, the more we lack information, or the more information deficit that we are. So the way to reduce the information is to gain, or the way to reduce uncertainty is to gain more information. And information is defined as the capacity to reduce uncertainty. So basically, the more uncertain you are, the less the information that you have. And the more information you have, the less uncertain you are, and so on. Entropy and randomness are kind of related. So entropy is often described as a measure of disorder or randomness. But this can be, unfortunately, sometimes misleading. So in one example, which is showed here by Jeff Phillips on YouTube, which is a TED Talk, you can see an example where there are two glasses, one of them with ice cubes and one of them with just normal water. And he asks you about the entropy of these two, let's say, examples, which one has higher entropy and less entropy. So most of the people generally tend to say the ice cubes have a higher entropy, while in reality, they actually have lower entropy, and the normal water has higher entropy. So in information theory, Claude Shannon, he's the one who basically, let's say, defined or put a proper definition of how we can actually quantify this entropy or uncertainty. So what Claude Shannon says, he said, let's assume that there's a memoryless source with some sort of alphabets, as you can see over here on the screen, from A1 to AN. And each of these symbols has its own probability, so P1 to Pn. So this is the probability associated with knowing that the next, let's say, alphabet is A1, and Pn is the probability associated with knowing that the next alphabet is An, and so on. So how much information do we get when finding out that the next symbol is A of I? It's actually related to the probability of that specific symbol. And according to Shannon, the self-information of AI is defined as the logarithm of 1 divided by the probability of symbol I. So what does this mean? Basically, first of all, we have to say why we are using probabilities, because a measure, like a probability measure of uncertainty, it's basically, think of it like if you have a probability of 0, it means that this event is impossible to occur. While if you have a probability of 1, it means that we are very certain that this event is going to happen. So a measure P of E of uncertainty about event E ranges actually from impossible, which is probability equals 0, to certain, where probability equals 1. So what Claude Shannon tried to say over here is that if you know that there is a high probability that something is going to happen, so you already know that is going to happen. So you are not gaining much information. And if you put it at the denominator rather than numerator, so the larger the probability it goes, then the amount will be smaller because you're not gaining information. And what he said, when the data source has a low probability value, i.e. when a low probability event occurs, the event carries more information surprisingly than when the source or the data source has a higher probability value. So again, if the event has a higher probability, then we are not gaining much information. And if the event has a low probability, we are actually gaining like more information. So it's like opposite case to the amount of information, or like basically the uncertainty in that probability. So you put the pi at the denominator and you take the logarithm of 1 over the p of I. And that's how self-information is quantified according to Shannon. Now, by using the logarithm definition, you can simply say this is actually equivalent to log 1 minus log p of I. And log 1 is what? 0. So you end up with minus log p of I. So that's the first step in quantifying this amount of uncertainty, or let's say information in general. So let's move forward and see how to generalize this concept. So what Claude Shannon defined is the entropy, as you can see over here, and this is generally known as Shannon entropy, which is a measure of information which is defined as the number of bits to represent the amount of uncertainty or randomness in a data source. So the general equation, as you saw previously, we got like logarithm of 1 over p, and we said that's equivalent to minus log p of I. So that's the minus, that's the log p of I. You just multiply it by the p of I, and that's the summation of all the probabilities. That is actually your entropy. So where there are n symbols, so the summation goes from I equal 1 to n, each one of them with a probability of occurrence that is equivalent to p of I. This is how you quantify the entropy or the uncertainty related or associated with that specific variable that you are looking at. So in this case, you can quantify the uncertainty or the entropy of individual variables, okay? Because as you saw, each variable will have a number of samples, or if you want to think about it in terms of time series. So the time series will have a number of values that occur at instances of time. And then you need to know the probability that each value will occur. And then you can like estimate the entropy. So how are we going to do that? Let's take it step by step. So as we said, given a discrete random variable x with possible outcomes that go from x sub 1 to x sub n, occurring with a probability of p of x of 1 and p of x of n, the entropy is defined as you can see over here. So the first thing that we need to do to calculate this entropy is to think about where am I going to get the p of I, or p of x of I, or in general we say just p of x. And because you are talking about one variable or one time series or one feature, we are actually looking at p of x, and we usually call this the marginal probability. Okay, keep this in mind. So when you work with one variable, it's marginal probability that you need to estimate. Now, to simplify the concepts, instead of just giving you information about entropy and mutual information and how they both can be used in machine learning, let's actually take one example and work it out together. So the example that I'm considering over here today is based on the IRIS dataset. So IRIS dataset is one of the very famous datasets in machine learning. It has 4 features, or let's say 4 variables, if you just want to call them, stick to the like features. Let's say terminology. So there's feature 1, 2, 3, and 4, and there is a class label. In the IRIS dataset, the first 50 samples, they belong to class 1, so they have a class label of 1. The next 50 samples, they belong to class 2, so they have a class label of 2. And the third 50 samples, they belong to class 3. So the way to estimate the probability is by using a histogram approach. So assume that you took one of these features. This is one example. The way to work out the probabilities based on the histogram approach starts with basically finding out the minimum and the maximum in this time series or in this feature. So denote the minimum and the maximum and work out the range, which is the maximum minus the minimum. Once you work out the range, you have to select the number of bins. As you know, histogram is made of a number of bins. How do you select the number of bins? This is a tricky question, because if you end up putting so many bins, you will have issues with the estimation of the entropy and mutual information. It won't be much accurate. And if you don't have enough samples, So what are you going to do? It's not going to be accurate again. So this is something tricky that we can talk about later on. So basically, find the range, specify a number of bins for your histogram, and then divide the range by the number of bins. So what you end up doing is partitioning that range into 10 equivalent bins. So in this case, the minimum in my example over here is 0.1, and the maximum is around 2.5 for this specific feature. What we are going to do is that we are going to partition that space, or that, let's say, limit from 0.1 to 2.5 into 10 equivalent bins, equivalent in terms of size. And then what we are going to do to work out the probabilities is to check how many samples in the original time series fall within this range of 0.1 to 0.34. And then put the number over here. So you can say, for example, 40 samples, just as an example. And then you move to the next bin. You say how many samples from the original time series or from this feature fall within the range of 0.34 to 0.58, and put the count of these over here, which could be 30, 20, whatever, and so on. If you continue doing that, you will calculate the number of samples that will fall within the range of each of these bins. So what you have done, again, you worked out the range, you specified a number of bins using the histogram approach, and you divided that range into equivalent bins. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bins. So I divided that range into 10 bins, and I started calculating how many samples out of my feature fall in each of the range of these bins. So you can see in the first range, I have around 41 samples. In the second bin, I have around 8 samples. In the third bin, I have around 1 sample, and so on for the remaining bins. So how is this going to help me figure out the probabilities? Right now, we are talking about histogram and count of number of samples. Well, if you look at the feature, originally, you know that there are in total 150 samples in this example. So what we are going to do, divide the number of samples in each of the bins that you see over here by 150. And by doing that, you end up with your required probabilities. So these are the probabilities that the feature value fall within the range of this bin, the range of the second bin, third bin, and so on. And if you have these probabilities, you plug them in this equation, and you will have the entropy associated with this variable or feature or time series. So the P of i's that you see over here, first of all, there are 10 of them. So I will go from 1 to 10 because there are 10 bins. And this is P of 1, P of 2, P of 3, P of 4, and so on. So all what you need to do is to plug in the value of P's in this equation minus summation P log P. And that's your entropy for this specific variable. So this is one of the simplest ways to calculate what? The entropy. Now, for all of the 4 features, I have 4 features. I've done the same. I've calculated the histogram again for the different features. And I'm showing you the histogram here with the bins. You can go ahead and repeat the process. So divide by 150 because you have 150 samples. You turn these counts into probabilities, and you plug in the values to estimate the entropies. So eventually it will look something like this. So the probability of the first feature across the 10 bin, probabilities of the second feature across the like 10 bins, and so on for the different features and the bins. Plug the values for each of the rows, which means for each of the feature in this equation, and you will get 4 values which represent the entropies of the individual features, feature 1, 2, 3, and 4. So each one of them will have its own specific entropy or uncertainty. So what do we do next? The idea over here is that information is actually depicted, let's say, as the difference of uncertainties. So the information is the uncertainty before knowing an event minus the uncertainty after having an event. So in this case, if I want to link it to the, let's say, idea of variables or features in my case, I had the entropy of the individual features. So where's the information concept coming from? How do I link that? What is the event? What is before and what is after? So the uncertainty before is represented by, let's say, for example, by the entropy of the individual features. And then for each of the features, you will start looking at the joint entropy, like what is the entropy of feature 1 when I knew that there is something known as feature 2? What is the entropy of feature 1 when I consider feature 3? What is the entropy of feature 1 when I consider feature 4? And so on for the remaining features. So from now on, from this step forward, what I really need is not only the entropy of the individual features, not only the entropies that you see over here, but I also need the joint entropies. Why? Because then I can say what is the uncertainty before minus the uncertainty after, and that's how I get a measure of information. So let's simplify it further. Now we need to think about something which is called the joint entropy. So the joint entropy of two discrete random variables, x and y, is merely the entropy of their pairing, which is the x and y. So basically, the entropy of x and y, if you think about it as a chess game, so x and y could represent the position of the chess piece, so on the row x and on the column y. Then the joint entropy of the row of the piece and the column of the piece will be the entropy of the position of the piece. So eventually, when you work out your new probability, which is no longer the probability of p of x only, but probability of p of x and y. So if you multiply p of x of y times the logarithm of p of x of y and take the summation across the x and y with a negative sign, you will get the joint entropy. Now, keep in mind, previously, we were looking at the entropy of the probability of individual, let's say, events or individual variables. And at that time, we utilized something called the marginal probability. Now we are actually using something which is denoted as p of x and y, which is denoted or known as the joint probability. It's no longer marginal, it's the joint probability moving forward. So how do I estimate the joint probability distribution? I know that I need that p of x and y. How do I estimate it? I know that for the individual variables, I built some sort of histogram and I defined the number of bins and I quantified how many samples exist in each of the bins. But how do I do it for two variables? Well, simply do it for two variables together. So you can estimate this equation or this amount, h of x and y. But how exactly can I do that? Let's show the example again. So the previous example, we had one variable or one feature with a range starting from 0.1 to 2.5. What if I bring another variable with a different range, which could start, for example, from 1 to 6.9? The idea over here is that instead of using one-dimensional histogram, I will build two-dimensional histogram. So you can see that in the x-axis, I will have the limits of the bins of the first variable. In the y-axis, I will have the limits of the bins for the second variable. And then all what I need to do is that I will go and look at the values of the features. And I will say how many values from the first feature fall within the range of 0.1 to 0.34, while the values from the second feature fall within the range of 1 to 1.59, and I'll write that number over here. Then I'll go how many variables from the first feature fall within the range of 0.1 to 0.34, while the values from the second feature fall within the range of 1.59 to 2.18. I'll write the values over here, and so on. I will continue filling in all of these values together. Once I do that, I'll end up with something that looks like this. Okay, a two-dimensional histogram, for example. Once I have the counts of how many samples fall within each of the bins, again, I'll divide by the total number of samples, which is 150. And then my p of x and y will be what? The values that I get from here, from each of the bins. Just sum them all. using this equation, P of X and Y log P of X and Y, and that's your joint entropy. So now I had the entropy of the individual variables, and now I calculated the joint entropy of each two variables, X and Y, not only one of them at a time. Now, what do I do with these entropies, or how do I exactly get the amount of information from the definitions of these entropies? First of all, let me tell you that in information theory, we use the concept of Venn diagram to represent the entropies. So in general, what we do, we use a bunch of circles in Venn diagrams. We use a bunch of circles to represent the entropies. So this is the entropy of the variable X, we denote it as H of X, and this is the entropy of another variable, which is H of Y. Because the two circles are completely separated from each other, these two variables, X and Y, they are actually independent from each other. There's no relationship between the two because the circles are completely non-overlapping or separated from each other. So the variables are independent. When there's a relationship between the two variables, what will happen is that the two circles or the two balls will start to overlap. So you remember we said initially that the orange circle is the entropy or uncertainty about X. We call that H of X. And the blue circle is the uncertainty about our variable Y or feature Y, and we call that H of Y. Now, the joint part between the two of them, if I can draw that over here, this joint part is the amount of information that each of these variables know about the other. Well, that was a bad drawing, actually. Let me just erase it, but you get the concept. So that ion of X and Y, this one, is how much X knows about Y and how much Y knows about X. Now, after knowing that there is a relationship between these two variables, you are actually reducing the entropies. So what happens over here is that the remaining part of the orange circuit is the uncertainty left about X after knowing Y. So after knowing Y, there is still some sort of uncertainty, which is, I will quantify it to you exactly. So if I want to draw it in a nice way, I have to do that slowly. If I go around the circle and go like this, this is the uncertainty left about X after knowing Y. So why did the circle size change? Because that portion became known to us by knowing Y. Similarly, if I look at Y, the entropy of Y, we also reduce the entropy of Y by knowing X, because X covers a portion of Y. So the uncertainty left about Y after knowing X will be what? This portion. So this is the uncertainty left about Y after knowing X, and we call that H of Y given X. This is the uncertainty left about X after knowing Y. We call that H of X given Y. And the joint part, we call it the mutual information. So if I want to mark this part to you, this is the mutual information between X and Y, and we call that I of X and Y. Now, what I showed you so far, we started with the calculation of the marginal probabilities. We moved to the individual variables entropies, H of X and H of Y. Then we went to the joint probabilities and we calculated the joint entropy, H of X and H of Y. And now I'm telling you about the joint part, which is the mutual information between X and Y. But if someone asks, like, where is exactly the joint entropy of the two? So if we want to plot that, hopefully I'll make it in a nice shape this time. I'm using my mouse, so it's a bit difficult. And this is your H of X and Y, which is the outer frame of the two. So the outer frame of the two is H of X and Y. This is the uncertainty remaining about X after knowing Y. And this is the uncertainty remaining about Y after knowing X. And the joint part is the mutual information, as we said. It's important to understand how you read these terms and what each of them means or represent. So let's move a little bit more forward. So if you want to calculate the mutual information between X and Y, you can basically use the individual variables entropies and the joint entropy. So in one case, if I want to figure out how much is this exactly, because I have the three terms, h of x, h of y, and h of x and y, what I can do is that add the size of the orange circle to the size of the blue circle. And if you just add them together, both of them, you are actually considering this area twice. So if you subtract that from h of x and y, you will actually end up with the mutual information. So h of x plus h of y minus h of x and y. That's one way to do it. The other way to do it, to calculate I of x and y, is to get the size or get the orange circle and subtract it from h of x given y. So get all the size of the orange circle, subtract it from the uncertainty remaining about x after knowing y, you end up with this portion. Again, don't forget that we started from the individual entropies of h of x and h of y, then we calculated h of x and y, and now we are actually able to quantify how much is I of x and y. Now, what about if I want to calculate, if I need to calculate, for example, h of y given x directly from the joint probabilities? Well, yes, we can. If you have the joint probability, P of x and y, if you simply take the same equation as the entropy and divide it by the P of x, you will end up with a quantification of h of y given x. So let's move forward. If I push the two circles inside, like as you can see, I'm pushing from the outer to the inside from both of the sides. So I of x and y, that portion, that joint portion between the two circles will grow large. And by that, you are actually increasing the mutual information between I of x and y. So as you keep pushing the circles inside toward each other, you are increasing how much one variable knows about the other variable. So you are increasing the amount of mutual information. Now, one thing to pay attention to is that we keep talking about mutual information now, but you have to look or pay attention to the, let's say, the mark over here. What is it? Is it a comma or a semicolon? Why? Because it will make a difference. So let's keep that a little bit, like just delay it a little bit more until the next slide. So in addition to the previous measures, one might think, what if the two circles actually have different sizes? They are not of the same size. So when can that happen? Well, when one feature has way more states than the other feature. So the variance of one of them could be much larger than the variance of the other. For example, you will end up with the entropy of one variable being different from the entropy of another variable. So in many situations, people or researchers in general usually start using a concept which is known as the normalized mutual information. So how do I normalize mutual information? Again, pay attention to the semicolon. Don't forget the semicolon. How do I normalize the value of the mutual information? By dividing by what? The entropy. So if I want to tell how much is this joint portion that x knows about y and y knows about x, I have to, let's say, consider that with respect to the size of x and the size of y. And that's why we divide by h of y or h of x. So the two of them could be not equivalent or non-equivalent. And if you want more general representation, so the two coefficients have a value ranging from in the range of 0 to 1, but are not necessarily equal. So pay attention. That's because of the sizes could be different. So if you want a symmetric measure, in that case, what you can do is take the I of x and y and divide it by h of x plus h of y. Now, in addition to the representations that we have seen so far, where we had two variables and a joined portion, which we call the mutual information, we have situations where we have more than two features. Well, in most or in all of your machine learning problems, you actually have more than two features. You will be lucky if you have only two features, or maybe not, depend on your problem. So in this case, I have more values or more terms to worry about. So now that joint portion between x and y is still what? Mutual information between x and y. But when z came into the problem, things started to become more complicated. So now what I have over here is, if I look at this equation or this term, what it says, originally, the orange circle is still h of x, the blue circle is h of y, the green circle is h of z. What we are saying over here is that what is the uncertainty remaining about x after knowing y and z? So can you draw the boundaries of this entropy? And this is the entropy of y after knowing x and z. So can you plot that to me over here and quantify it? The joint part between the three variables, I, or mutual information between x, y, and z, is actually linked in this region. And then you still have one term. So originally, if I can plot over here, let me see if I can actually plot. Originally, when we had two variables, this portion used to represent the mutual information between x and y. But now things are different. I have a third variable. So what I really need to do is that I need to look at the mutual information between x and y given z. So mutual information between x and y given z. Can you actually plot that? I'll leave that as a homework for anyone interested to try. So how do I calculate the conditional mutual information? And by the way, we call this conditional because we say given there is something else, another factor. So that's where you start looking at conditional mutual information. Now, going back to my earlier note about the comma and semicolon. So if you go back in Stack Exchange or any of these websites and search for the difference, like what's the difference when someone writes it with a semicolon and or comma? So one of the interesting questions, which is asked by someone online, says, anyone can conceptually explain what is the difference between the term over here that you see I, X, Y, Z with a semicolon, or this one with a comma and then semicolon. So what do you think? What is actually happening when you use the different terminologies? So one answer is that basically I of X comma Y semicolon Z means the mutual information between what? X and Y together and Z. So when you see a semicolon, it's that the mutual information between everything before and everything after. So in another example, as you can see over here, I of X semicolon Y and Z means the mutual information between X and Y and Z together. The mutual information between X1, X2 semicolon Y1, Y2 means the mutual information between the two sets, the X's and the Y's. So be careful how you read the mutual information. Now, as you saw, mutual information is one of the measures that we can use to tell about the relationship between two variables. But can't we just use correlation? Well, you can, and the two of them complement each other. Like the two measures, the mutual information and correlation, they some sort of like give kind of complementary information, let's say. Well, some people might disagree. So let's look at the commonalities and differences between them. So mutual information is what? A weighted sum of the joint probabilities of the two random variables, while correlation is a weighted sum of the product of the two random variables. Mutual information measures the linear and nonlinear dependence, while the correlation measures the linear dependence only. Mutual information requires the knowledge of the distributions, which can be tricky because you need a methodology by which you can estimate the distribution. Well, correlation, which is based on covariance, can be calculated directly from the data samples. Okay. MI can be applied, mutual information can be applied on symbolic sequences as well as numerical sequences, while correlation can be applied on numerical sequences only. Mutual information can be generalized to consider conditional relationships. Conditional relationships is not an option yet, and basically not directly, with correlation coefficients. So if you look at the definitions, or like mathematical definitions of the two, each contains a pointwise measure of the distance of the two RVs from independence. So it's up to you to use either of them depending on what you really need for your problem. Now, why did we define everything that we have seen so far? We have seen the entropies of the individual variables and the joint entropies and the mutual informations. But how are these exactly used in machine learning? Well, in machine learning, one of the most important steps to build a machine learning pipeline or system is related to the concept of feature extraction. And feature extraction is generally divided into two steps. That is the feature construction and feature selection. In feature construction, you convert the raw data into a useful set of features, like, for example, mean, variance, average, whatever, like standard deviation, any kind of feature you can think of. Then feature selection is concerned with selecting the most important features for my problem. Those features that are really related or that can infer the outcome of the problem, and they are minimally redundant. So that's where we're going to use the concepts of entropy and mutual information when we start talking about feature selection as a dimensionality reduction method. So in machine learning, when you talk about relevance, we are actually quantifying the information content of a variable against the class label, if you're looking at classification problem, or against a regression outcome when you have regression problem. So that is known as mutual information between C, which is the class label, and X, which is a variable or feature. On the other hand, we also talk in machine learning about redundancy. And for redundancy, again, we are going to quantify the amount of information that is shared between a variable against another variable. And we denote that as mutual information between X and Y. So it's the same measure, which is the mutual information. If you use it between a variable and a class label, or a variable and a regression outcome, so that's called relevance. And if you use it between one variable and another variable, then that's a measure of redundancy. Again, we are using one concept, which is mutual information, but applying it between different variables to end up with either relevance or redundancy. Now, I've showed you before how to get the marginal probabilities based on the feature values. But what if I want to calculate it between two variables? So we showed that already. We said if you have the histogram of one variable, the histogram of the second variable, if you just build a 2D histogram, the joint probabilities, you can plug the values in this equation and you can get your mutual information directly. So no need to get the entropies first and then mutual information. I can plug the values of the joint probability and divide it by the marginal probability of X and marginal probability of Y and multiply it by this term, and I get mutual information between X and Y directly. So that's one good thing for us, is that I can calculate mutual information immediately once I have the marginal probabilities of the two features and the joint probabilities of the two features. I can plug these into this equation and get my I of X and Y. But what if I want to calculate the mutual information between a class label and the variable? Can I assume that we can use the same concept, like marginal probability of this variable and marginal probability of that and the joint probability? Well, if I have a class label, I can't really go and use, like, for example, 10 bins as I did over here. Because what if I only have, for example, 3 classes? So the maximum value that I can see is what? 3. The class label is crisp, discrete. It will be 1, 2, 3, the different classes that the samples belong to. So what can I do in that case? Well, you can actually use, again, a 2D histogram, but it's slightly different, okay? Or if you want to call it 3D, up to you. So this is the 3D bar plot, actually. So the number of bins, again, you will construct a histogram, but instead of saying how many samples from the feature, so I'm looking at one feature now, which is only X. And I'm saying, originally I used to say how many samples from this feature X fall within the range of the first bin, which used to be 0.1 to 0.34, something like that. Now what I'm going to say is that how many samples from this feature X fall within the range of the first bin while the class label is 1. And then how many samples from this feature X fall within the first bin while the class label is 2, the orange, and then while the class label is 3, the yellow, and so on. So now I have the bins as I did previously, but I'm putting another factor in, which is the classes. And the classes will only go 1, 2, 3. It's not going to go 1 to 10, so you can't assume anything. It will be limited by the number of classes in your problem. So this is what you're going to do for each of the features. So this is the first feature in the iris dataset. If I bring in the second feature and do the same, and look at the second feature, the distribution of this looks like a Gaussian. So I don't think this feature is actually good to tell me much about the different classes in the problem. And you can see that the distribution across the classes are pretty much like, let's say, convolved or overlapping with each other. Go to the third feature, you can see that the distribution started to clarify. And on the fourth feature, you can see very well distributed, let's say, feature values across the different classes. So now if I want to calculate I of C and X, I have the marginal probability of my variable X. So the equation again will be P of Cx log P of Cx. I need P of C and P of X. So P of X I have, P of C and X I also had, which is I calculated from here. What I need is P of C. But what is P of C? Well, it's simply the probability of the class. If you go back to the original data, we said 150 samples. Each 50 samples belong to one class. So if you want to quantify that, you have 50 divided by 150 gives you 0.3 something. Another 50 divided by 150, another 50 divided by 150, and so on. Now you have the terms required to calculate I of C and X, mutual information between a variable and the class label. What if I want to calculate the mutual information between two variables, X and Y, with the class label C? And notice the comma and semicolon, so I can really take these brackets away if I want. Okay, so you can work it out again, build the two-dimensional representation of the bins, and then divide that across class 1, class 2, class 3, and then fill in the equation with the values and calculate your I of C, X, and Y. So why do I need this? Well, it depends. I will show you why. So the problem over here is that feature extraction addresses the problem of finding the most compact and informative set of features. So again, feature extraction had construction and selection. So the idea over here is that when you extract a lot of features, some of these features might not, like individually, they might not be relevant to your problem. But when you put them in a subset within the context of others, you will find them really useful. And some features might be individually relevant or may not be individually relevant. But as I said, in the context of others, they may show to be really good. So you have to, let's say, select a bunch of features that are relevant and minimally redundant. So you don't want to select a lot of features that are relevant to the problem because you might find some of them are exact replica, for example, of the others. So what's the point? So that's where we're going to use the concept of mutual information between each two variables or each subset of variables together. Depends on what you're going to do exactly or which algorithm are you going to employ. And then a measure of redundancy as well. So relevance and redundancy. We need both of them. And mutual information can be used to help you estimate relevance, which is the relationship between each of the features and the class label, and redundancy, which is the relationship between one variable and another. So one of the very well-known algorithms for feature selection looks at building a subset where the features are maximally relevant and minimally redundant. So by maximum relevance, again, what do we look at? The information or the mutual information between each of the features, x of I, and the class label C. And for the relevance, we look at the mutual information between each two variables. So you want the I of x and C to be very high, but you want the I of x of I and I of like x of j to be minimum. So you want to reduce the similarity between the two. So one of the first like really well-known algorithms, as we mentioned, is the MRMR, which is maximum relevance and minimum redundancy algorithm. And what it does is that it uses the difference between I of x of sub j and C, which is mutual information between each of the features and the class label, and subtracting that from the summation of the mutual information between each two features. So how does this work? What we do in this algorithm is that, first of all, we look at the mutual information between all of the features and the class label and try to see which one has the highest mutual information with the class label. We put that in an empty subset. So we create an empty subset, we put that feature as the first feature in that subset. And then we bring in more features, but we bring in more features on the condition that the mutual information between these features that we bring after that should be minimal with respect to the already selected feature in the subset. And we continue bringing more features sequentially. So this algorithm is very well known, as I said, and has been recently used by Uber engineers to solve one of their problems and in one of their recent publications. And there are different implementations of this algorithm in Python, MATLAB, and C/C++. So go ahead, use any implementation. But the idea over here is that what we have shown you today is an approach, or to tell you about one very simple method by which you can estimate these values, I of x and c and I of x and x sub I and x sub j. So we have shown you one method by which you calculate the variables or the terms required to run this algorithm. So think about it as, let's say, the fuel for these algorithms. So the fuel over here is the mutual information between the variables and the class label and between the variables themselves. And then only you can run such an algorithm. So you can easily install this, pip install PyMRMR, and then you have it in Python ready. So go ahead and try it. Well, pay attention that this only came in 2005, but if you do a proper literature review, you will find another publication from July 1994 by someone called Roberto Battisti. He actually devised nearly the same algorithm with the difference over here before the summation. So again, this guy says, rank the features in the same manner, create an empty subset, start adding features to the subset by looking at the features that have the maximum mutual information with the class label and subtract that with the summation of the mutual information between the features and those like already selected in the subset that you are creating. So the two are very similar to each other. In another implementation, there is another like algorithm which is called the MIEF algorithm. This one extends the concept a little bit more, not only considering I of like mutual information between each of the features and the class, but each two features and the class label. And it actually showed like better performance than MIFS. So it's up to you to decide any of the algorithms. What we are showing you today is how to estimate the amount of mutual information required to fuel these algorithms or to enable you to run the different versions of these algorithms, regardless of which one you're going to end up using and who created what. This is where I said that Uber engineers have actually used the maximum relevance, minimum redundancy. So this algorithm resurfaced again after like many years of publication, and it's still one of the most heavily utilized feature selection algorithms. But instead of using mutual information, I believe those guys used correlation between the different features and the F-score to replace the mutual information between the feature and the class label. So use any measure that you want as long as it works for your own problem. It's up to you. We showed you one method to do that based on mutual information. Now, the conclusions over here is that, first of all, there are so many different ways where you can estimate the probabilities. I showed you one example, one very simple approach by using the binning approach or the histogram approach. But of course, the problems over here include the effect of the sample size. So if you don't have enough samples, that histogram wouldn't be like accurate representation. The number of bins, how to select the number of bins is another issue. And like you find a lot of publication criticizing the use of binning, but it's one of the simplest ways to explain the concept, like how do we estimate mutual information. Other algorithms like kernel density estimation, like Poisson density estimator or the K nearest neighbor statistic can be used to help you with the estimation of these marginal probabilities and the joint probabilities. So it's up to you to use whatever algorithm you are happy with. Finally, there are several feature selection algorithms based on entropy and mutual information that exist nowadays. It's again up to you to choose the right one by yourself. So what we really recommend you to do is that at least use a bunch of these algorithms on your own problem, feed them with the same mutual information values that you have estimated, and see which one of them will give you better performance. So at least run a couple of algorithms, do some sort of statistical validation, and then pick up one of these. So it's totally up to you which one you end up choosing. So I hope you have learned something new today on the concept of entropy and mutual information and how they can be used in feature selection and machine learning. Thank you very much.